Fusion Mobile, quality e-learning experience on the go.
Welcome to Fusion Mobile e-learning clinic. My name is Sonia Lalo and I'll be guiding you through the chemistry course. In this particular lesson, we'll be looking at metals and their compounds. Metals and their compounds. We'll start by looking at the properties of metals, then the extraction method for metals, and then we'll look at the group 1 metals and we'll concentrate on sodium at first. Then we'll look at the compounds of sodium, we'll consider potassium and its compounds. Then we'll go ahead to group 2 elements and we'll talk about calcium. We'll look at calcium and its compound, and then we'll talk about also magnesium and its compounds. Then we'll go to group 3 elements where we'll talk about aluminium, and then group 4, the compounds of aluminium. We'll then talk about group 4 elements where we'll talk about tin and compounds of tin, as well as lead and its compounds. So let's begin. When we talk about metals and non-metals, we've always had the mentality that metals are hard, non-metals are rather not hard. Well, the difference between a metal and a non-metal is all about the ionization of the substance, the ionization of the element. What do I mean when I say ionization? When a particular element wants to come into a stable form. We've been talking about elements liking to be in stable form. When they want to be in a stable form, some of them do lose electrons, some of them do gain electrons. So, for a metal, for it to become for any element rather to be in a stable form, it has to ionize. It has to ionize, which means it would either lose some electrons or it would gain some electrons. For metals do lose electrons, while non-metals, they do gain electrons. But then there are some properties that are common to all metals. We have them written all over here. We have based on their physical appearances. Metals generally have a high boiling point. They are characteristic luster. They are malleable. Well, let me point out something before we go on. There are two metals that are actually very, very odd. They do not behave like most metals do, and those are hydrogen, which is a gas, and mercury, which is a liquid in atmospheric condition. Mercury and hydrogen, they are the odd ones. So the two odd ones are hydrogen, which is a gas at room temperature, and mercury, which is a liquid at room temperature. All other elements, all other metals exist as solid at room temperature. Now, they are malleable, which means that they can be ironed into sheets. They can be hammered into sheets. They can be flattened. They can be compressed. Also, they are ductile. When I say a particular metal is ductile, it means it can be drawn into wires. They can be pulled and stretched, and they will not break so easily. Also, and as well, they have a sonorous sound. When you hit them, they produce a kind of a unique, a distinctive sound, kind of an interesting sound that blows your mind, sort of. Yes, they are hard, but they are not brittle. They are hard, but they are not brittle. That is, they have strength. And when we talk about brittleness, it means when they drop, they just break. They are not like that. They don't break so easily. They have very high relative densities. Compared to other substances, that is the non-metals, their relative densities are quite high, and they are very good conductors of both heat and electricity. Of course, because of their availability of free valence electrons, which have different orbitals within which they can move. They are free to carry electrons, charges, either for heat or for electricity. Okay, let's look at their chemical properties. The chemical properties include, the first thing is their ionization behavior. They ionize by electron loss. They ionize by electron loss. They are generally reducing agents. When you see them take part in any chemical reaction, any redox reaction, you see them either giving away electrons or kicking out, you see them behaving like, you see them giving out electrons, which is actually what we know metals for. Also, in acids, when they react with acids, they liberate hydrogen. Well, this is the only condition where you find, you actually see a metal trying to behave like a non-metal, as in trying to oxidize a particular system, because we know that it is a displacement. We also know that reduction is also the addition of hydrogen to a system, but this time around it is a removal of hydrogen. Well, it looks like an oxidation process because we are removing hydrogen, but that is the nature of metals. Metals are higher than hydrogen in the electrochemical series, will replace hydrogen in its acid. Also, if you look at the nature of their oxides, when you burn them and they produce oxides, their oxides, most of them are very stable, but their oxides are basic in nature. Their oxides are basic in nature, and the oxides form bases, either alkalis or other bases. So these are some of the chemical properties of metals. All right, let's compare the properties of metals generally. Of course, we have been talking about the electrochemical series. We've been talking about the activity of metals. We just spoke about substances, metals higher than hydrogen in the electrochemical series, displacing hydrogen from water. So what happens? In a short while, in a very few seconds, you see the table on your screen. Yes. Okay. From the table, we can see there that when it comes to different metals, as you go down the electrochemical series, electrochemical activity decreases. Chemical activity decreases, electropositivity also decreases. Look in terms of combustion, you find out that the topmost ones are readily combustible to form in air to form oxide. The middle ones actually form oxides when heated in air, while the bottom ones they do not react with oxygen. That's nitrogen and silver and gold. They do not react with oxygen. Also, you see the displacement of hydrogen in water, in heat, or in steam, while so many of them do not react with water. The reactions with HCl, the reactions with tetraoxosulfate 6 acid, the reaction with the trioxonitrate 4 acid. Also, we'll consider their solubility in water, their stability, their oxides, their hydroxides, their trioxocarbonate, their trioxonitrate 5s, their solubility in other substances other than water. And you see another table right now which is talking about their reactability and the process, the amount of energy that is required, that is given off in the electrochemical series. And we'll see hydrogen being very unique, having 0.0 because as a standard electrode potential. Why is that so? Because it is set as a kind of a standard to which other elements are being compared. Alright, we've talked about metals generally and their behaviors. Let's quickly take this short break. Let's take this break now, and when we come back, we'll look at we'll look at them one after the other, that is group by group. We'll talk about the extraction first, then we'll consider the group by group thing. But before we go into that, during this short break, some questions will be displayed on your screen. Please answer them. Want to see what you've understood so far in this lesson. Thank you. Welcome back. So let's quickly consider extraction of metals. Let's consider extraction of metals. How do we go about the extraction of metals? Well, we know that metals are abundant in nature. We find them underneath the earth crust. We can excavate them just like we do our research and our explorations, and we pull out our petroleum. We also have solid metals, solid minerals which can be harnessed from the earth crust. Now these solid minerals contain different types of metals depending on what particular substance you are harnessing, we are exploring from the ground. For example, if you explore limestone or substances like that, you have abundance of calcium in it. So when we harvest these substances, how do we extract the metals from it? Well, there are about a couple of different ways, a few ways that this can be done, but the first processes to undergo would be the cleaning of the metal. Now, how a particular metal is being cleaned differ from metal to metal, but there are still some general methods that are common to them all. We have for solid metals, we have the cleaning of you clean them usually using pressurized water to take off the excess soil particles around them and purify them to get the real thing out of the depths. After cleaning with jetted water, oftentimes warm water, after cleaning, then we go ahead to do what is called roasting in air for most of the metals. Why do we roast them in air? Because we want to get the oxides of these metals. It is easier for us to try to separate the oxide from the metals in certain conditions, though, than when we try to separate it from other compounds that they may contain. So we do what is called the roasting in air, and after roasting in air, then on some of them, now this is where we have to go separate ways. Some of them do actually after roasting in air, they can be separated by thermal decomposition, some of them by chemical decomposition, while some also would require electrolytic decomposition. So depending on the reactivity of the particular element, the type of decomposition and the nature of the element, also the type of decomposition would be chosen as appropriate. So this is how we go about the extraction of metals. The group 1 metals, the group 1 elements are all known to be metals, with an exception of hydrogen, which does not fully behave like a normal metal, of course due to its existence in the gaseous form. All other members of that group, such as lithium, sodium, potassium, and the rest of them, have metallic properties, and all exhibit these properties in terms of their appearance and the kinds of chemical reactions which they do partake in. So let's take sodium as our focus in this particular lesson. Of course, they all have one outermost electrons, that is, they are univalent. When they ionize, they have just one electron in the outermost shell, which they can actually release. And the ionization energy reduces as you go down the group. When we talk about ionization energy, it simply refers to the energy required to remove one electron from this particular element. The energy required to displace one electron from the element. Now, if you take note, all these metals react with water, although at different under different conditions. Lithium and sodium react violently even with cold water. Potassium, not so violently. Other metals might require you to heat up the water, and some of them might actually require you to heat up both the metal and the water before a reaction can take place. Alright, let's look at the physical properties of sodium. Sodium has a silvery appearance. Of course, a solid with a metallic luster. It has a relative density of about 0.98. This suggests that it is lighter than water, hence it would float on water. It is very malleable and very soft. Of course, for it to be that malleable, it must be soft, and it has a low melting point of about 97 degrees Celsius. It is also a very good conductor of heat and electricity. Let's consider sodium and its chemical reactions. So when we burn some sodium in air, because of its reactability, it will react with oxygen to form sodium oxide. It reacts with oxygen to form sodium oxide. And this sodium oxide, when it is diluted in water, it will form sodium hydroxide, which is the base form of sodium. But also, if you burn sodium in the presence of excess air, you would be able to produce what is known to be sodium peroxide. Sodium peroxide. Apart from oxygen reactions, sodium also reacts with other compounds, especially non-metals, though metals and non-metals alike, and it reacts in addition reactions. So it can join itself to chlorine to form sodium chloride, and also it reacts with water to liberate hydrogen and produce the base. It also reacts with acids to liberate hydrogen and to produce the salt, and it reacts with ammonia to liberate hydrogen. You see, every time it sees hydrogen, it displaces hydrogen. This is because it is higher than hydrogen in the electrochemical series, and such is for other members of the group 1 elements. They are basically higher than hydrogen in the electrochemical series. So they usually displace hydrogen in almost everywhere they see it. Alright, when we talk about sodium, what are the uses of sodium? Sodium is very, very important in the production of many reagents in the chemical lab. We also use it for lighting different locations, especially in the airport where very good lighting is required. Also, we use it as a coolant. We use it as a coolant for nuclear reactors because nuclear reactors radiate a lot of heat energy. So the sodium is used to curtail, to control the energy, and it is also used as a very good. It is also a very, very good reducing agent. It's a very, very good reducing agent. How do we test for the presence of sodium in a particular substance? Well, when you have a particular substance and you suspect it to be sodium, very easy test. All you need to do is take the substance and you burn it in air. When you burn sodium in air, it gives a golden yellow coloration. A golden yellow coloration, a bright golden yellow flame. That's what it burns with. It burns with a bright golden yellow flame. Now, if you take your blue glass and you put it on to look at this golden yellow flame, it will become invisible. The golden yellow flame is invisible under blue glass. When you burn potassium in air, if you suspect something to be potassium, when you burn it in air, you observe a lilac flame. But when you view this lilac flame under a blue lens, blue glasses, you would see a crimson coloration. So unlike sodium, where it burns with golden yellow and you look at it and it just disappears, you can't see it. In potassium, when it burns lilac. When you look at it under a blue lens, it is crimson. Alright, let's look at the compounds of sodium as we go on. We have sodium can form many different compounds depending on what it reacts with. And the first one we'll consider is the sodium oxide. Sodium oxide is produced simply by burning sodium in air, and we have sodium oxide. Sodium oxide reacts with water and produces hydrochloric acid. It produces sodium hydroxide. Not hydrochloric acid. It produces sodium hydroxide. Sodium hydroxide, when you mix sodium oxide, when you mix it with water, it reacts violently with cold water. But if you accidentally add it to an acid, it is explosive. So we are always very cautious around sodium oxide. Let's talk about sodium peroxide. Sodium peroxide is produced by burning sodium in the presence of excess oxygen or in the presence of excess air. So when we produce sodium peroxide, it reacts with water to liberate oxygen. It reacts with tetraoxosulfate 6 acid to produce hydrogen peroxide. Reacts with tetraoxosulfate 6 acid to produce hydrogen peroxide. And what are the uses? It is used to produce dyes. It is used to produce dye. This sodium oxide is a colorless solid, and sodium peroxide is a pale yellow liquid. Alright, let's progress. Pale yellow solid. We have sodium hydroxide. Sodium hydroxide is a base. It can react with different substances, like all bases do. It can react with CO2 to produce salt and water. It can react with ammonium salts to release ammonia. It will react as an hydroxyl precipitator. It will precipitate out certain metallic hydroxyls which are heavy, like lead. Also, it reacts with metals to liberate hydrogen, just like other bases do. Obviously, it reacts with acids to produce salt and water, which depend on the acids. Now, also, let's quickly look at our sodium chloride. Sodium chloride is produced by reacting the acid and the base, that is sodium hydroxide and hydrochloric acid. We react them together and we produce sodium chloride. Well, the uses of sodium hydroxide, this is used for analyzing and preparing certain reagents. So let's consider the uses of sodium hydroxide. Sodium hydroxide is used for analyzing and preparing certain reagents. It is used in soap making. It's also used as a bleach for bleaching cotton materials, for refining of petroleum produce, and also it can be used to absorb CO2. When you want to take out CO2 in a particular region, you can also use your sodium hydroxide. Let's quickly talk about sodium chloride. Sodium chloride is produced by the reaction of sodium hydroxide and hydrochloric acid. So when you react them together, you have sodium chloride produced and water. Of course, our sodium chloride is consumed as salt. It is used as our normal table salt. When it is pure, it is not delinquent. It's not delinquent. When it is pure, it is not delinquent. But we tend to see that when we leave our salt in a particular place, it becomes moist after a while. That's because of the presence of magnesium chloride in it. Magnesium chloride is delinquent, and they are both white substances. So sodium chloride is edible. It is used as a food additive and a food preservative. It's also used in the manufacturing of many different reagents in the laboratory, especially sodium related materials. It is used in regenerating water softeners, resuscitating them, restrengthening them, bringing them back to activity. Of course, let's quickly look at sodium tetraoxosulfate 6. Sodium tetraoxosulfate 6 is an important salt. It can be produced by reacting sodium chloride with tetraoxosulfate 6 acid. A displacement reaction would occur. Sodium tetraoxosulfate will be produced, and HCl, that is hydrogen chloride gas, would be liberated. So when this occurs, this particular salt is also used for making of dyes and many other important substances. When we talk about sodium trioxonitrate 5, sodium trioxonitrate 5, it can be produced in the laboratory by reacting sodium chloride with trioxonitrate 5 acid, and that will produce this particular salt, sodium trioxonitrate 5. But the salt, under heat, it decomposes to liberate oxygen and produce sodium amide. Soda amide. Alright, the production of sodium trioxocarbonate 4, the production of sodium trioxocarbonate 4 is described in a particular process known as the Solvay process. The process begins with the compression of ammonia gas, carbon 4 oxide, and water. When they are compressed together, they form a particular compound known as the ammonium trioxocarbonate. The ammonium trioxocarbonate would be, the ammonium hydrogen trioxocarbonate. The ammonium hydrogen trioxocarbonate will then be reacted with sodium to form sodium hydrogen trioxocarbonate. This sodium hydrogen trioxocarbonate would be heated and it would decompose to form sodium trioxocarbonate and give up water vapor and carbon dioxide once again. Now, this particular substance is deliquent. It crystallizes with a water of crystallization. Yes, it crystallizes with it is hygroscopic, not deliquent. It's hygroscopic. It crystallizes with the water of crystallization without it becoming a liquid, without it diluting itself. So it will absorb the water for it to crystallize, and its water of crystallization is 10 moles of water. All right, this particular process is known as the Solvay process. By now, a particular diagram should be on your screen to show the setup for the Solvay process. All right, let us look at the only important. What are the uses of sodium trioxocarbonate 6? Sodium trioxocarbonate 4. Well, sodium trioxocarbonate 4 is very, very important because it is used in the making of glass, especially water glass. It's used in manufacturing of glass. It's used in the making of soaps, in making of detergent, in paper making. It's used as a water softener. It's used as a standardizing agent for acids. It's used for the standardization of acids, and it's also used as an analytical agent. It's one of the reagents that we use to analyze materials, metals, non-metals, to check what is present and what is not. Okay, well, this particular compound that we talked about, the sodium hydrogen trioxocarbonate, sodium hydrogen trioxocarbonate 4, is the only and the most let me not say the only, it is the most important of all the hydrogen trioxocarbonate 4s, because it is very, very important in the production of trioxocarbonate 4, sodium trioxocarbonate 4, and also it decomposes. It decomposes in the presence of HCl to give us sodium chloride, water, and liberate carbon dioxide. All right, let's quickly take a study of what happens to potassium's compounds. There are many compounds of potassium, but let's just take these 3 in quick session so we can understand how many of its compounds do work. Potassium, we'll talk for a starter, we'll start with potassium chloride. Potassium chloride can be found in natural states in combination with other metals, other compounds, other salts, especially magnesium salt in a particular compound known as carolines. The carolines, well, it can be processed, and we can extract the potassium chloride from it. In the laboratory, it can be produced by simply reacting potassium hydroxide with sodium chloride. It can be produced by reacting potassium hydroxide with hydrochloric acid, and that would result into the production of potassium chloride, and water will be given off. Potassium chloride is important for the production of fertilizers, and it is also used in the development or preparation of many potassium compounds. Well, also it is good to note that there is also the potassium tetraoxosulfate 6. While trying to produce potassium tetraoxosulfate 6, you use potassium chloride reacted with hydrochloric acid, tetraoxosulfate 6 acid. When this reaction occurs, it will go through an intermediate state of the production, which involves the production of potassium hydrogen tetraoxosulfate 6, which means it will produce an acid salt before it will go ahead to produce the final salt. Well, the acid salt is not so much great importance, so we will not be looking too much into that. As well, we know that we can produce the nitrile, which is potassium trioxonitrate 5. It can be produced by simply reacting potassium hydroxide with the trioxonitrate 5 acid, which will involve potassium trioxonitrate 5, which is also known as the nitrile. Now, this nitrile is very, very important. It is used as a preservative in the market. It is used in the making of some certain explosives. It can mix it with certain other explosive materials to make a big bomb. Potassium triazonitrate 5 can be produced by reacting potassium hydroxide with triazonitrate 5 acid, which will produce potassium triazonitrate 5 and water. Potassium triazonitrate 5 is very important. It is known as nitrile. Nitrile. It is one of the major components for making gunpowder. It's also used for making explosives, as well as it is used as a preservative, a food preservative in the market. Okay, let's quickly look at the group 2 elements, and we'll place our focus on calcium. Well, the group 2 elements are all metals. They're all metals that contain elements such as beryllium, magnesium, calcium, strontium, barium, like that. This particular group of elements are known as the alkaline earth metals. They all form basic oxides. They have basic oxides, and they have very interesting properties. But let's look at one of them, which is calcium, as our focal. Let's take calcium as our focal point. So for calcium, the physical appearance of calcium in its natural state, it is silvery gray, solid. It has a relative density of about 1.55, which means it is denser than water, and that means it will sink. It is malleable and ductile, and also it has a relatively low tensile strength. It has a melting point of about 851 degrees Celsius. I remember the other time we were talking about sodium, we said it had a melting point of about 97 degrees Celsius, and we said it is very low for a metal. Yes, metals can be 800, 900, even 1500. Alright, it's a very good conductor of both heat and electricity. Let's look at the chemical properties, chemical reactions that calcium naturally undergo. Well, calcium reacts with air. It bonds in air to produce calcium oxide, which can react with water to produce calcium hydroxide. It engages in combination reactions with non-metals such as chlorine, oxygen, fluorine, nitrogen, even hydrogen, and it forms salts of their kinds, or hydrides. It reacts with water. It reacts with cold water very slowly, but when the water is warmed up, it reacts more rapidly with warm water, and it liberates hydrogen, produces the calcium hydroxide. It also reacts with concentrated H2SO4 or other acids, just like every other metal, to liberate hydrogen and produce the salt. It reacts with ammonia to liberate hydrogen and produce calcium nitrate. So let's look at how do we test for the presence of calcium in a particular substance. Well, when you take a particular substance and you suspect it to contain calcium, when you put it in a flame, if it is burnt in a flame, it has an orange-red appearance. But when you use a blue glasses to look at it, it will be brick red. It will appear as brick red, but it's of course orange-red appearance. The same thing when you take your barium and you test. You want to check your barium. Barium is Ba, not Br. That's bromine. Barium. Your barium. You want to test your barium. You put it in flame. You see a pale green appearance. And the strontium produces a bright red appearance. Okay, let's go ahead and look at the compounds of calcium. Then we can proceed. There are very many compounds of calcium. We'll look at a few of them. The first we'll talk about is the quicklime. That's calcium oxide. Calcium oxide can be produced either by burning calcium in its natural state in the presence of air, or simply by burning calcium triazocarbonate 4, which is the most available form of calcium. You can burn it in air. You can heat it up and to about 900 degrees Celsius. It will disintegrate and form quicklime and carbon 4 oxide. This reaction is reversible. So if you allow the carbon 4 oxide to go away, you can have your quicklime. Now, quicklime has very many uses. It is used in the manufacturing of cement, of calcium carbide, of even glass, and very many interesting substances. We use quicklime for their creation. We also use quicklime as for reducing the acidity of soil. The acidity of soil. It is a cheap base, so we can afford to buy it and use it to neutralize the soil. Also, we can use it. It is used in the industry for neutralizing acidic wastes. It is used in the industry for neutralizing acidic waste, and it is a reagent that is used in the drying of ammonia. It is a reagent used in the drying of ammonia. Let's quickly look at slack lime. Slack lime, that's calcium hydroxide. Calcium hydroxide, slack lime. It can react with carbon dioxide and produce produce limestone and water. So slaked lime, as this pronounced, is also very important. It's also very useful. It is used also for soil treatment. It's also used for soil treatment. It is also used in the making of mortar for buildings. The making of mortar for construction works. It is used in the preparation of ammonia. You can use it to recover the ammonia that has been evolved or liberated from the survey process, so that you can reuse that ammonia for other functions. It is also used as a bleaching agent. It's used as a bleaching reagent in the laboratory. It is also used as a bleaching agent. It is used as a bleaching agent in the laboratory. Okay, let's look at calcium chloride. Calcium chloride can be produced by reacting limestone with hydrochloric acid. When the reaction occurs, it will liberate carbon dioxide as a waste product, produce water and calcium chloride. Calcium chloride is soluble in water, and it is used as a drying agent. It is used for drying most gases, except for ammonia. It's not used for drying ammonia because there is a chance that the ammonia will react with the chlorine in the calcium chloride and it would form ammonium chloride. So we don't use it for drying ammonia. We rather use our quicklime or our slaked lime to dry ammonia. But for other gases, we do use calcium chloride. It's very important reagent in the laboratory. We also have the calcium tetraoxosulfate 6. Calcium tetraoxosulfate 6. It can be produced by reacting calcium chloride with sodium tetraoxosulfate 6. A substitution reaction will occur and they will switch. We have sodium chloride will be produced and calcium tetraoxosulfate 6 would also be produced. Now, this calcium tetraoxosulfate 6, yes, the calcium tetraoxosulfate 6 is anhydrous. It is hygroscopic. It is hygroscopic. It absorbs water, and when it absorbs water from the environment, it absorbs moisture from the environment, and it hardens. It hardens, and it is used for making what we know as the plaster of Paris. The plaster of Paris, that's POP, which is used for people who have injuries, bone injuries. It is used to make casings for injuries, especially that's in medical line. It's also used in the beautification and construction. It's used for making molds for casting of objects. Okay, let's quickly look at the calcium nitrate. That is the calcium trioxonitrate 5. The calcium trioxonitrate 5 can be produced by reacting calcium oxide with the trioxonitrate 5 acid, and that will produce calcium trioxonitrate 5 with water. Now, calcium trioxonitrate 5 is mixed with slaked lime to form a fertilizer. It can be mixed with slaked lime to form fertilizer. Before we go, let's quickly consider the most important of all the calcium produced, and that is limestone. That's calcium trioxocarbonate 5. calcium trioxocarbonate 5, we look at all the experiments we wrote on the board, we see it occurring almost every time. We see it reoccurring to show its importance. It is used in the production of almost all calcium compounds. We use it in the production of almost all calcium compounds. We also use it for cement making, for making it can be found in different substances such as limestone, such as quartz and other calcium storage substances, because in the earth crust, that is how we find it existing in natural state, existing as trioxocarbonate mixed with other compounds to form this either limestone, quartz and other substances like that, marble. So for us, it is a very, very, very important material used in the production of very many things such as cement, as chalk. It's even used in the production of certain fertilizers, just to mention some of its uses. Okay, let's quickly take a look at magnesium and magnesium compounds before we go to analyzing the group 3 elements. For the extraction of magnesium, magnesium chloride fused with sodium chloride has to be electrolyzed. It has to go through an electrolytic process, and during this electrolytic process, one of the products that will come out of it is pure magnesium. We find magnesium existing in nature in many compounds of salts, either in the trioxonitrates, yes, or in the trioxocarbonates, that's trioxonitrate 5s, or the trioxocarbonates 4s, or even in the tetraoxosulfate 6 salts. But let's look at magnesium as a substance. Magnesium as a substance, it exists as a silvery white solid. It has a relative density of about 1.74. It is malleable and ductile. It has a melting point of 650 degrees Celsius, and it is a good conductor of heat and electricity. Chemical reactions it partakes in, it burns in air to produce magnesium oxide. It is a very good reducing agent. It reacts with tetraoxosulfate 6 acid or any other acid for that matter to displace hydrogen as other metals do, and it does react directly with non-metals. What are the properties? What are the benefits or uses of magnesium? They are used for preparing light alloys of compounds. Light alloys. They are used as antioxidants, and they are used in making fireworks, firecrackers, and the likes of them. Minute, small explosives. All right, let's look at compounds of magnesium. We'll take into consideration magnesium sulfate, that's magnesium tetraoxosulfate 6. It is produced by reacting magnesium oxide with tetraoxosulfate 6 acid, which will result into the production of magnesium tetraoxosulfate 6 and water. Magnesium tetraoxosulfate 6 is a deliquescent salt, which means it needs a water of crystallization to crystallize, and when it crystallizes, it forms a white salt known as the Empson's salt. This Empson's salt finds a lot of use in the medical line. Also, we have the magnesium trioxonitrate 5. The magnesium trioxonitrate 5 is produced by reacting magnesium or magnesium oxide with the trioxonitrate 5 acid. This reaction produces magnesium trioxonitrate 5 salt and liberates hydrogen, or when magnesium oxide is used, it produces the salt and the water. Of course, also this salt is not stable in itself. The salt is not stable in itself. It needs a water of crystallization, and the water of crystallization required is 6 molecules of water of crystallization. Now, this particular substance, that's magnesium trioxonitrate 5, when it is subject to heat, it dissolves, it loses its water of crystallization, and the anhydrous form of it is unstable. It decomposes. The anhydrous form of it is not stable. It decomposes in the presence of heat. It decomposes in the presence of heat, and it gives off magnesium oxide, gives off also sodium. It gives off magnesium oxide. It gives off oxygen and also nitrogen 4 oxide. Okay, let's look at the group 3 elements and their properties. So let's consider aluminium. Aluminium group 3 elements generally. Group 3 elements have 3 valence electrons in their outermost shell. They are metallic. Of course, they release their electrons, and they release their electrons because to get electrons to fill their outermost shell, they will need a minimum of about 5. That's a lot. So they let go of electrons, and majorly they consist of aluminium. We can also see in that particular group boron, aluminium, and the rest of them, tellurium, and the others. So in this particular group, what are the features? Let's concentrate on aluminium since it looks like the heavier ones the more. You will notice that aluminium is actually a solid at room temperature, a silvery white solid. It has a relative density of about 2.7, which is still low. It is very malleable and very, very ductile. It can be drawn into wires, can be rolled into sheets. It can also be, it is moderately tense, which is good. And actually, when it is alloyed, it becomes even stronger when it comes to in terms of its tensile strength. The tensile strength is moderately high, but when it is alloyed again, it becomes even better. The melting point of aluminium is around 660 degrees Celsius, and it is a very, very good conductor of heat and electricity. Let's come to the chemical properties of aluminium. Aluminium reacts with air to produce aluminium oxide, and also that's with the oxygen in air. It also reacts with the nitrogen in air to produce aluminium nitrate, aluminium 3 nitrate, of course. It reacts with chlorine and other non-metals in direct combination reactions to produce different salts. It also reacts with acids to liberate hydrogen. It reacts with ion 3. It displaces ion 3 from its oxygen and becomes aluminium oxide. It forms aluminium oxide and displaces ion. Okay, let's quickly look at the uses of aluminium. We use aluminium for making our cooking utensils, our cooking pots, our spoons, our kitchen equipment. Most of them are made from aluminium, made of aluminium because of the nature of aluminium. Aluminium is non-corrosive. It does not corrode, so we can use it to make food related things. You can use it for cooking, and since it's also a good conductor of heat can also easily pass through it. It is used as overhead cables. It's used for making overhead cables. Of course, it's a very, very good conductor of electricity, and overhead cables are it is cheaper. Aluminium is cheaper than copper, though copper is a better conductor of electricity. But since aluminium is cheaper and those overhead cables will run for very long distances carrying very high voltage, aluminium can do that. Also, it is used in paint making, for making paint, especially oil paints. We use aluminium as one of the components that is mixed together, and in the alloying of metals for corrosion. When you want to alloy a particular metal to increase the strength of the metal against corrosion, aluminium is a very, very good material to consider. And also it is used in making welding powder. The welding powder is believed to clean, purify the metal about to be welded, and so that when the welding is done, it can be properly welded. So the aluminum oxide actually is used for making that particular powder. All right, let's look at some of the substances that some of the compounds of aluminium. We'll talk about aluminium oxide. I mentioned it a couple of times. Aluminium oxide can be formed by the decomposition of aluminium hydroxide, and that will produce aluminium oxide and water. So aluminium oxide is very, very useful. It forms an abrasive substance, an abrasive solid, which can be used as for abrasive purposes. It can also be used as an adsorption substance in chromatography. It can be used as an adsorption substance in chromatography. It is also being used as a catalyst. while cracking hydrocarbons. It is used as a catalyst while cracking hydrocarbons. Well, swiftly to talk about aluminium oxide, aluminium hydroxide. Aluminium hydroxide reacts with sodium hydroxide. It reacts with sodium hydroxide. It can react with both acids and bases. So it is amphoteric in nature. It is amphoteric in nature. It can react with both acids and bases. When it reacts with bases, form a stronger base. When it reacts with acids, it will form a kind of salt and water. Also, aluminum hydroxide is very, very useful. It helps dye to stick to a cloth. When you add dye to your clothes, it is aluminum hydroxide that helps it not to fade off easily. Let's talk about aluminum chloride. Aluminum chloride reacts with water to produce aluminum oxide and hydrogen chloride gas. Aluminum oxide and hydrogen chloride gas. So what is so special about the aluminum chloride? Aluminum chloride is used for a couple of reactions. Aluminum chloride is quite different from other metallic chlorides. Other metallic chlorides are formed due to ionic bonds, but aluminum chloride does not form ionic bonds. It's formed due to a covalent bond. So when it enters into water, it actually reacts with water, unlike other salts which do ionize in water. Aluminum oxide, of course, reacts with tetraoxosulfate 6 acid to produce the alum, that's aluminum tetraoxosulfate 6 salt and water. This compound alum, we know, of course, many of us know alum, potash alum. You put in your water in your house when you feel the water contains some dirt, and it actually coagulates the dirt and separates it from the liquid. So that's one of the major functions of alum. And that's it about aluminium and group 3 substances. Let's go ahead to look at the group 4 elements. When it comes to the matter of the group 4s, we discovered that these group 4s, I earlier told us in one of the earlier classes that they are filled with metalloids majorly. Well, they also have metals, especially because of the introduction of the transition group, and that kind of like moved our metalloids towards the right hand side of the table, making germanium, which happens to be in group 5, a metalloid. But then let's look at it. The first group members of group 4 are carbon and silicon, which we have discussed before now, so we'll not be talking about them anymore. We're looking at tin as one of the members of group 4. So let's consider tin. Tin has a silvery appearance, silvery white appearance with luster. It has 3 different allotropes: the gray tin, the white tin, and the rhombic tin, with different densities. Gray tin is about 5.76 gram per cm cube. White tin, which exists between about 17 degrees Celsius and 150 degrees Celsius, exists 116 degrees Celsius rather, exists as 7.28 grams per dm cube in terms of relative density, while rhombic tin, which exists above that temperature, exists as 6.6 grams per dm cube in terms of density. Also, all the allotropes of tin are fairly strong in terms of their tensile strength, and the melting temperature of tin is 232 degrees Celsius. It is a very good conductor of electricity and heat. Chemical properties: tin reacts with oxygen at about 1200 degrees Celsius to produce oxygen. Tin 4 oxide. Tin 4 oxide. It reacts also with chlorine as well as other non-metals. It reacts with chlorine as well as other non-metals to produce a kind of salt of itself. It also reacts with hydrochloric acid to produce a salt, liberates sulfuric acid, sulfur 4 oxide and water. It also reacts with tetraoxosulfate 6 acid to produce the salt, liberates sulfur 4 oxide and steam. Okay, let's consider the oxides and substances that are formed of tin. We have tin 2 oxide. Tin 2 oxide. Tin manages to survive in 2. That's ionization point of 2, and we see it reacting with oxygen again to form the tin 4 oxide. Tin 2 oxide is it's not so stable. It's always looking for an opportunity to react to form the stable form of tin 4 oxide. Tin oxide. What are the properties of tin? Tin is used for coating metals, steel, so as to make them corrosion free. You get your steel. Maybe you want to use the steel to do a particular job. You want it to be corrosion free, so you get your molten tin and you dip your steel in it so that it can become coated. It will become coated with the steel, with the tin, and it becomes corrosion free. It will not corrode. And also it is used in making corrosion free alloys that can withstand corrosion, especially when you need it to also possess certain qualities such as lightness and weight and the likes. Alright, let's proceed to tin 4 oxide. Tin 4 oxide reacts. It behaves, yes. Tin 2 oxide is an amphoteric gas. Is an amphoteric solid. It's an amphoteric solid. The same thing with tin 4 oxide. All tin substances are amphoteric. They are non-basic. That is, when they say they are amphoteric, it means they can react with both acids and bases. So tin 4 oxide reacts with tetraoxosulfate 6 acid to produce a salt and liberate oxygen. And also tin 4 oxide is used in the making of white emerald and tiles. White enamel is used in the making of white enamels and tiles. We have also tin 2 hydroxide. Tin 2 hydroxide, of course, it will react with, it is also amphoteric. It will react with other hydroxide to form stronger bases. It will also react with acids to form salts and water. So it can react with both of them. Also, when you react tin with the hydrogen chloride gas, you burn tin in the presence of hydrogen chloride gas, it will produce what is known as the tin 2 oxide and liberate hydrogen. The tin 2 chloride. Tin 2 chloride is one of the existing forms of tin, and tin 2 chloride is not so stable as that. So tin 4 chloride is produced when you burn tin in the presence of oxygen, chlorine. You burn tin in the presence of chlorine and excess quantity. It leads to the production of tin 4 oxide. The 4 oxide is also being produced, and our tin 2 oxide is used for preventing area oxidation. Is a salt that can prevent area oxidation, so you put it across the surface. The same thing as tin 4 oxide, it prevents oxidation of substances. Also, your tin reacts with other non-metals, even hydrogen. It has the tin hydride. This tin hydride is not so stable. It can be decomposed by heating the substance to a very high temperature. Okay, let's consider lead. Lead is also a member of the group 4. So considering lead this time around, we see that lead it is grayish white solid with luster. It has a relative density of 11.3. That is quite dense. It is very malleable and soft. It can even be cut with a knife, just like your normal leather chair and all. It is ductile, but not ductile enough to be drawn into wires. When you pull it, it breaks after it has a fairly strong tensile strength, and it has a melting point of 327 degrees Celsius. It is a very good conductor of electricity and heat. Chemical properties: it reacts with oxygen to form oxygen 2 lead 2 oxide. It reacts with oxygen to form lead 2 oxide. It could react with oxygen to form a unique structure, a unique form of it called the dilead 2 oxide. It can be, when it is subject to excess, when it's subject to a temperature of about 450 degrees Celsius, it produces diled 2 lead 4 oxide. Diled 2 lead 4 oxide. And that is this particular unique structure you can see over there. Also, it reacts with both acids and bases. It is amphoteric in nature, and it reacts with acids, that it produces salts and water, liberating whatever is needed to be liberated. If it reacts with hydrochloric acid, it will liberate the hydrogen chloride gas. But here it does not react with alkali. It is too low on the electrochemical series. It cannot displace any of the alkaline members. Alright, let's also look at the different structures in which it exists. This is lead 2. The lead 2 oxide. In lead 2 oxide, it reacts with acids and as well reacts with bases. Lead 2 oxide, lead 4 oxides, even lead, all the oxides of lead are amphoterics. They are amphoteric. They react with both acids and bases. When they react with bases, they form stronger bases. When they react with acids, they produce salts and water. The same thing with the the lead hydroxide. It reacts with other bases to form stronger bases, and reacts with acids to form salts and water, of course. So we have the lead 2 oxide, the lead 4 oxide. We have the dilead 2 lead 4 oxide. We also have the lead hydroxide, the lead nitrate. Now let's talk about lead nitrate a bit. Lead nitrate is it reacts with sodium chloride to produce lead chloride, lead 2 chloride. Now this lead 2 trioxonitrate 5, lead 2 trioxonitrate 5 reacts with. It also can have the lead chloride. You can have lead 2 chloride. You can also have the lead. You can also have lead 4 chloride. Lead 4 chloride can be produced by reacting lead 2 chloride with can be produced by reacting lead 2 chloride with chlorine. But this particular process it decomposes under for it to be produced, it should be done at a temperature of 0 degrees Celsius. But when the temperature rises above 0 degrees Celsius, it decomposes back to where it came. So these are the kind of reactions in which lead do take part in. So what are the benefits of lead? What do we use lead for? Lead is used in making roofing sheets, roofings. It's also used in for gas and water piping. Why? Because lead does not react with water. It does not react with gas. It is very, very unreactive. It reacts with selected substances. It will only react with water when it is heated. In fact, the lead must be in red hot state. The steam must be, of course, steam is red hot already. So, or superheated if possible. It is also used in making bullet casing because of this density. It is used in making accumulators, lead accumulators. That's batteries that we use in some of our devices. We also use it in making lead components, lead compounds, and substances like that. And lead is also a good reagent, a good substance that is used in radioactive environments, because it has the capacity of stopping the gamma ray or any other radiation for that matter, depending on how much of the lead is made available. It can prevent further exposure to radiations. Alright, we've come to the end of this particular lesson. In this lesson we considered metals and their compounds, a long one, where we talked about the properties of metals. We looked at the basic properties of metals. We then went to talk about the extraction of metals, basically how metals are extracted generally. And then we'll talk about group 1 metals, where we spoke more about sodium being the first metallic member, or rather the second metallic member after, of course, lithium. We didn't talk about lithium because it is too reactive and we don't usually use it in reactions. We don't classify hydrogen as metallic because of its state of existence in the gaseous state at room temperature. We also talked about potassium, looked at some of the compounds of potassium. We then went to calcium, which is a group 2 metals, and we talked about calcium. I said some things about magnesium. We went to group 3 and we took aluminium as our focal point, and then we talked about group 4 elements, where we talked about the tin and lead, since we've discussed carbon and silicon in earlier lessons. Okay, there have been a lot that has been said in this particular lesson, and there should be so much questions. So in a short while, some questions will be displayed on your screen. Please do well by attempting them. And if there is any of the questions that prove to be problematic, you can go over the video one more time for clarification. Thank you.